Good afternoon, everyone, and welcome to the Future of UV-EB, Advanced Manufacturing, Trends, Strategies, and Applications, a regular webinar series presented by the State University of New York College of Environmental Science and Forestry in collaboration with RadTech International North America, the Association for UV and EB Technology. My name is Sean Nicholson, and I will be your host today from SUNY ESF. As a reminder, all webinars in this series are archived at esf.edu/outreach/UVEB-webinar. In partnership with RadTech, SUNY ESF has developed an education and training program that is online and self-paced to accommodate the busy schedules of industry professionals and students. Below is a list of the fall course offerings. Visit our webpage, radgearing.com, for additional information. Today's webinar, entitled Implementing Atmospheric Plasma to Improve Adhesion of UV LED Curable Coatings, will be presented by Sarah Bauer. Sarah has 6 years' experience as a surface treating application specialist with Enercon Industries. Sarah assists clients looking to improve adhesion on a wide variety of materials, applications, and industries. Her knowledge of plasma and flame surface treating technologies and how to best implement them into production environments provides her clients with the insights they need to be successful. She is also involved with numerous industry organizations and most recently presented a technical paper on surface treating at the SPE Antech conference. Sarah earned her bachelor's degree from St. Norbert's College in De Pere, Wisconsin. Please help me welcome Sarah Bauer.
Thank you for the introduction, and thank you everyone for being here today. I appreciate it. I'm going to go ahead and start the presentation, and we will have some time at the end for questions and answers as well. So once again, the title of today's webinar is Implementing Atmospheric Plasma to Improve Adhesion of UV LED Curable Coatings. And here's my information. My contact information will also be available at the end of the webinar if you'd like to contact me directly. I'm going to do a quick overview of what we're going to talk about today, and then we'll dive into each of these particular topics. I'm going to start with just going through some emerging applications for UV LED cured inks, coatings, and adhesives. We're going to specifically focus on coatings, but of course inks and adhesives are in that same family when we're working with curing as well as looking for better adhesion to the surface of a substrate. I'm going to talk a little bit more about how plasma treatment is going to help adhesion to different substrates. We're all working with different materials and that's changing on an everyday basis. How you actually go about selecting the plasma and flame treating equipment. Then how are you going to integrate it into your existing or maybe new operations or applications. And then, of course, we also have some advancements in the plasma treating realm that I want to go over in a little bit more detail. And then there'll be, once again, some review and question and answer towards the end. So I'll just start by giving a little bit of overview on Enercon. That is whom I'm representing today. We, if you're not familiar, we're based in just north of Milwaukee, Wisconsin. However, we have locations in the UK and India as well. We are a family-owned, first-generation family-owned company, and we're established in 1974. We work with quite a wide variety of industries out there. We work in the packaging, of course, the films and flexible materials, the converting as well as the extrusion end. But we also get into a lot of plastics, assembly, automotive, medical. We have an entire division dedicated to induction sealing, so putting the foil induction sealing to a bottle as well. So that our range of applications is growing on a daily basis, and with that comes a lot of expertise to help customers with their adhesion challenges. We are an innovator in these technologies, and we have quite a few years of experience between all of us here that can help out. So I'll start by talking a little bit about the applications for curing inks, coatings, and adhesives using UV LED technology. I have a couple slides here, courtesy of Excelitas, that I'm going to use to kind of just do a quick recap. All of you probably are in different levels of familiarity with UV LED curing, but just kind of as a recap for everyone. There's some really for that the UV LED market is offering. As all of our applications and parameters change on a daily basis, new products are designed, we're working with more and more challenging materials. The need to bond and instantly cure is becoming more and more of an on-demand feature in our manufacturing process. LED curing really does offer that. We're getting away from our water-based adhesives and coatings that have long cure times. We need to reduce the cycle times, which the LED market is really allowing us to do. You're able to get that instant bond, that instant cure, whether it be an adhesive or a coating to the surface of a material. With that also offers some really great things such as a cure on demand or having a varying degree of cure. One of the new market technologies I was just researching even just this last week was that soft touch kind of UV cured coating. So having the degree of control of cure is also one of the benefits that LED offers customers. Of course, there's an energy savings going with LED lamps over maybe your more traditional mercury bulbs. We all know that your investment in the equipment is going to quickly pay itself off in reduced energy consumption. And of course, with that, you also have a smaller footprint. So, maybe able to get rid of a drying tunnel or a longer conveyor process or a secondary process where everything needs to sit and cure for a longer period of time. It's taking up valuable floor space. That floor space could be used for something else. We're all paying taxes, heat, and cooling for that floor space. So being able to eliminate that from the process is a huge added benefit to so many different technologies, so many different industries out there by going with this technology. And of course, single component systems, so getting away from a multi-part mixing of adhesives or coatings and being able to simply put a single component on the surface. Not only does that reduce your, once again, physical footprint of the equipment, but it also it allows you to move a little quicker in your process. And of course, environmental. We're all trying to be greener in this world. We're trying to decrease our emissions, decrease our carbon footprint, and using LED curing allows us to do that. We're getting away from the ozone generation and also looking with low flammable materials as well. So from a safety standpoint for both our employees, those who work around this equipment, as well as from a cost savings of insurance. In regards to the applications, there's basically it kind of falls into two different categories. So we've got spot curing and we've got area curing. Area curing is probably going to be more applicable to the coating end, spot a little bit more to the adhesive end of things, but you're also going to see quite a few overlap of those two different types of focal points here. So I listed a couple different applications in the field: catheters, medical devices. You'll see a lot of technology-driven applications as well. But we are working with a large variety of technologies as well as materials here, and this definitely illustrates that as we think, okay, where is LED going to be a good fit, and then what are our next challenges going to be moving towards that? So kind of talking a little bit more into those specific emerging applications, medical devices is a huge market that Enercon works with, as well as a lot of our UV LED partners on the field. Catheters, the business of manufacturing and developing catheters is huge. It is something that we here at Enercon see on a daily basis. We're working with insulin pens and other kinds of advances in medication delivery systems. With that, however, comes our challenge of using plastics that we've never used before, or using recycled plastics even. Printing, more specifically to UV curing of printing, is also becoming a little bit more of a challenge, working with different inks and ink color formulations, being able to print quicker. Think of high-speed lines where we need to be able to print quicker and cure quicker. Has challenged the UV LED market as well as the surface treatment market as well. And being able to create sufficient power to meet those speed demands. With LED, there is some limitations on the types of power level that you can, so the wavelengths you can get. UVA is definitely an emerging technology, but the UVB and UVC is yet to come and follow behind. So with those different speed demands, is that we know that a lot of our customers have challenges in order to go to UV LED. So that kind of ties back into, okay, so we've got this new technology, great. Now what are we going to do? We have these different plastics, we have these different materials, but we have a dynamic going on here. Yes, we can cure that ink, that coating, that adhesive to the surface using the correct LED wavelength and the photoinitiators to cure. But what about the actual dynamics of it bonding to the surface? And that's really where Enercon comes into play and helps solve those adhesion challenges, because what we do know about UV curable coatings and inks and adhesives is that it does require what we call a very high surface energy and a very prepped surface for good adhesion and cohesion. So some of the dynamics that we deal with different materials, and I say plastics a lot because it's a very common material we work with, but we do work with metals, we work with organic materials, composites, we work with wood, we work with a lot of different materials out there. So if you're not just in the plastics world, it's okay. Most likely we've probably worked with your material as well. Actually, food products, to be honest, we've also worked with that as well. But asking, what is the material type? What are we working with? What are the factors that come into play? What's the polarity of the substrate? Is this substrate going to be very accepting of a UV cured ink? Are we using the right kind of UV cured ink or coating adhesive? Is the chemistry something that's going to create a problem for adhesion? Let's think of a fluoropolymer, and I'll get into that here in a little bit in more detail. But we're not really going to have the right chemistry between those two. And how are we going to make something that is designed to not let something stick to it ultimately stick to it? The roughness, it actually has quite a big factor in adhesion. The smoother the surface is, not just to the naked eye, but on the microscopic level, the more difficult we're going to have a time actually bonding to the surface because it doesn't have a lot of surface area. And then, of course, the bond stress. What kind of product are we working with? Is this a decorative product and it's okay if the ink were to scratch off or the coating were to scratch off later on? Or is this going to be under a lot of stress? Is this going to be an aerospace? Is this a medical device that cannot fail? And it kind of asking us taking all those things into consideration and asking ourselves, what are we ultimately looking to achieve will help us determine what route we want to go. So for those of you who may not be familiar with surface treatment and what it does, I'll kind of go over that a little bit here in more detail. I mentioned before the goal is to get good adhesion. And with that is we basically want that liquid. Let's say in this particular slide that you want that liquid, could be a coating or an adhesive, to wet out as much as possible. We want that droplet before it is UV cured to grab onto the surface, go from being a hydrophobic to a hydrophilic surface, and wet out as much as possible so that when that adhesion, that curing occurs, that we have the best surface contact possible. So here's just kind of a good visual graphic of what our challenges are. Low surface energy, we typically refer to this as dyne, D-Y-N-E, if any of you are not familiar with dyne level. That actually measures the energy of the surface of the substrate and will typically give us a good indication if we're going to be successful in adhere something to the surface before or without treatment. And then our goal ultimately is to increase that dyne level. Contamination, we're dealing with different types of mold release, contaminants. If we have a metal object, for example, we might be dealing with some residual oils or other contaminants on the surface. So removing them via a plasma or flame treating technology is going to help that UV coating to adhere better. Something migrating to the surface. This is huge in the medical industry. We have a lot of plasticizers and things that are put into the plastic in order to keep them pliable. Well, those also can become a barrier to getting good adhesion because you're not truly bonding to the material, you're bonding to that additive. limited bonding sites I mentioned is where you actually are physically trying to adhere to a very smooth surface. It can be difficult. And once again, you have a very hydrophobic surface. That ink coating or adhesive is staying in a very tight droplet on the surface before you treat. There's some other options, of course, and I'm sure all of you are at least familiar with one or more of these. We've got liquid primers. It's a chemical. Of course, getting away from chemicals is everyone's goal, so we've got, a hazardous material. We've got the cost associated with that, and we're not moving towards a greener and leaner production or process. We've got mechanical preparation, so things such as physically roughening the surface. If you were to take sandpaper and sandblasting or some other kinds of roughening mechanisms are one way to create more surface area to adhere to. But obviously this has wear parts, it's messy, there's more cost time, it's not very precise as well. Another technology out there is what we consider a vacuum plasma, and a vacuum plasma is where you have more of a chamber-like style treater. You put the part in, you shut the door, and you treat the part. It bounces around the chamber in a very crude way to explain it, and you're going to treat all of the surface areas that are exposed to that plasma. Downside to that, however, is it's a batch process. So this is a very time-consuming process. The equipment itself is quite an investment on your part, and as you increase production, everyone wants to be leaner and move and have something that's done in line, and you're not going to be able to do that with a vacuum plasma system. So the alternative, of course, is an atmospheric treater, flame or plasma, which is what Enercon manufactures and what I'm going to focus the talk on today. So I'm going to talk a little bit more in detail about how a plasma is going to promote adhesion. It's basically in the most basic sense of what is plasma. It's charged ions. It's ionization of a gas of some kind. That gas could be air. It could be a noble gas of some kind, and it could be used in conjunction with a natural gas or propane, as is the case with flame plasma. They're basically broken down into a couple different types of plasma. You'll see here on your screen that you've got a photo of a blown ion plasma to the left. That is just air that's ionized, and what you see coming out of it, while it looks like a flame, is just ionized air particles that are bombarding the surface. The blown arc plasma system is a little different. You'll see a little different treatment pattern as there are different requirements from other applications in the field. This also is ionized air that you see coming out of there, an alternating current between two electrodes. And then the one on the right-hand side is a flame plasma. So we're using natural gas or propane in conjunction with air to create a very high velocity discharge to do basically three things. We are cleaning, functionalizing, and micro-etching the surface. And I'll go into a little bit more detail on that. So to start with, cleaning. I mentioned early on that sometimes you're dealing with contaminants, especially working with metals, but once again, could be mold release or other contaminants on your part. If the surface is not clean, you're ultimately just bonding to that contamination. So it might initially look like you have a good bond after you've UV cured, but you might find via crosshatch test or what other kind of a tape test or other methods that you're using that it's truly not bonding to the substrate. It has cured. It's cured very nicely to the contaminant. So plasma allows you to remove that without any kind of chemical wiping, IPA wiping or whatnot to the surface, or perhaps a bath of some kind, and remove that step and that we'll call element of human error out of your process. The second thing that it does is it micro-etches the surface. So to the naked eye, you don't actually see a difference between a treated versus untreated surface. You shouldn't. But on a very, very microscopic level, you've created more physical surface area. So an optimized surface area is kind of illustrated on this screen where you're creating more peaks and valleys. So if you can envision here your coating being laid out over a more roughened surface with more peaks and valleys on it, you've actually created more physical surface area for that to grab onto, and you've also created an opportunity for more polar groups for that ink to adhere to as well. While you're not actually changing the substrate itself in any kind of physical form, you're not weakening it in any way. This is, once again, keep in mind, an extremely microscopic photo of the surface. It also helps you with getting good adhesion. And then the third piece that we're going to do is functionalize the surface. And this is where we use the term dyne level. That's one way of measuring the functionalization of a surface, but ultimately increasing those polar and nonpolar groups on the surface so that when you adhere, let's say, a coating that tends to be more of a polar coating, and maybe you're working with a material that tends to have more nonpolar groups, by functionalizing it, you're going to actually bring out more polar groups in the surface because you've got more physical surface area. That is also going to create a more wettable area, and you're going to get better bond strength between the two. And here's just a quick photo of a trial of a film, a polyethylene film, both before and after treatment on quite a magnified scale, but you'll see that it's physically roughened on the right hand of the screen versus the left. And so you would, to the naked eye, you would not see this, but your coating would see this, which is ultimately what we want to achieve. So just a kind of quick recap here, what we're dealing with is an adhesion impediment, low surface energy, contamination, migrating additives, and very hydrophobic slick surface. Our goal is to create a higher surface energy or higher dyne level, get rid of that contamination, remove the migrating additives, create a more roughened surface, and ultimately create a more hydrophilic surface for that ink, coating, or adhesive to wet out. And with that, we're going to actually get a better cohesion and adhesion of that ink, coating, or adhesive to the surface of your substrate. And here's a quick illustration of it. Another term you might be familiar with, if not, I can definitely explain it, is a contact angle measurement. The contact angle measurement is actually the angle of the substrate to the ink, adhesive, or coating and relative to your surface. So our goal with treatment is to decrease that angle as much as possible in order to get good adhesion. So this is actually a really good test method. It does require a piece of equipment, but it measures that decrease in angle on a surface that is non-porous as well as a flat surface. The surface does have to be flat to some degree to get that contact angle measurement. Some examples, this is definitely not an extensive list of everything we work with, but they're more common materials. I mentioned the word dyne level. For those of you who are not familiar with it or work with it every day, this is a measurement of the actual surface energy of the substrate. You'll see that our initial dyne levels are not always the same. No ABS or peak or PET is always the same. Coming in, it can be related to if it's recycled, it could be related to how old it is, how it's manufactured, if there's any other additives in the mix. But you ultimately see that post-treatment levels also have a range of outcomes, and that is related to the material and where it started. It's also related to how we treat it, not only technology-wise, but also dwell time and power level. And here's another chart of some additional materials that we work with. I pointed this out early on, but fluoropolymers have a very low surface energy. So for example, PTFE, which falls into that category, has an initial dyne level that's under 30. It's a very hydrophobic material, but we do basically need to treat that material in order to get any kind of UV curable adhesion to it. Even with some of the best formulations of inks and coatings, typically with that such a low surface energy starting dyne level, it needs to be used in combination with some level of treatment. Other materials have a higher starting dyne level. It's kind of more dependent up to the application and if you're going to need surface treatment. And, sometimes you get this question of, how much are we going to increase the bond strength? So this was an adhesive that we cured in some test results related to a polyethylene substrate. But in general, both the blown ion system from the previous page as well as our flame plasma system, you can increase your bond strength by about 3.5 times what you'd be dealing with without. This is going to vary a little bit substrate to substrate, but just to kind of give you a quick snapshot, it's really a nice, has a nice synergy with using UV curable inks and coatings and adhesives. I'll kind of go over a little bit more on the actual technology and how we help customers decide, what's going to be the best fit. kind of a shameless plug here, one of the neat things about working with Enercon is that all of the treaters that we manufacture are atmospheric. They're not the vacuum plasma that I referenced before. The reason why that is our goal is to keep you moving. We want this to either be introduced into an existing process and not be another step, or as you develop a new process that it's going to be right in line with a conveyor, a turntable, a robot, even in a lab environment. We want it to be just used right away prior to the UV curing application. And with that, we have quite a few different types of varieties of atmospheric treating technologies. And one of the nice things is by looking at more than one, not just focusing on one specific type of technology, you may find that there's more than one suited for your application. And I'll go into how we determined that. So I mentioned earlier, what's the material of the part? There are certain materials we know right off the bat are going to be better suited for others, and that's kind of where our sales expertise and tech team really can come in to help you with your application. One of the limitations to certain types of atmospheric treating is if the material is conductive or non-conductive, or if the material is going to be near a conductive fixturing. Some of these technologies do not like to, they cannot treat anything that is conductive because it is a floating current, and some of them are internally grounded, so we don't need to worry about that. The area that needs treatment. Are we bonding a needle into a needle hub? Is it a very, very tiny area that needs to be treated prior to the UV adhesive applied, or are we treating the side of an airplane, or are we doing something in between? You'll see lots of different head designs, and some of them are more conducive to different types of applications than others. How is the part handled? A lab style, a turntable, a conveyor, all applications that you can overcome with different technologies. How fast you need to go. Obviously, our automotive partners out there know that cycle time is huge. There's a lot of other industries where that is in the forefront of their thinking as well. So we have to make sure that the technology that fits with the application is going to be able to keep up. And this is obviously true at the UV curing side as well. A very important question to ask on the front end when selecting your equipment. And then ultimately putting it to test in your lab. We do have a lab where we're able to treat with all of the different technologies, atmospheric technologies, to potentially give you one or more solutions. I'll go in a little bit more detail on each of these. The blown arc air plasma system, some of you might look at this and say, oh, that's a corona system, which is another term for it. It's a great system. It's a very tried and true technology. You can't see it from this picture, but there's actually two little electrodes in it, and there's an alternating current bouncing between the two. And what we're using is compressed air to push through those two electrodes to create what we call an arc. You'll see that the treatment pattern's a little wider with it. It's also great for very heat-sensitive materials, or more of a slower process, or a more call of a lab or small batch process as well, because we know that the system's limitations are that it cannot treat in a very high speed environment, and it also cannot treat anything that's conductive. So that's why this particular technology is really good for once again, small batch processes, and also a wider treatment. It might need to be printing on, let's say, a 3-inch area. This would be a very, very good fit for it. Kind of the complementary or sister to that technology is what we call the blown ion air plasma. Once again, we're just using air and we're ionizing that through a nozzle. You'll see that it's a much more concentrated discharge, and one thing actually I'm really glad we have this photo up, that a lot of customers ask me and say, oh, you're treating a circuit board, isn't that going to interact with the electronics on it? And the answer is no. It's actually internally grounded, so what you see that actually comes out of there is just the ionized air, and it's not going to arc to anything. It's a very aggressive technology. It does a very good job of cleaning. It works around metals and as well as plastics. It's able to kind of reach inside of areas. So I mentioned needle hub bonding, for example, earlier. That would be a very good fit for this technology. And it can go and can handle some pretty high speeds. Another couple applications out there is any kind of 6-axis robot for following a glue path. This is a great system for it. A wire and cable marking, or marking on the sides of different kinds of bottle lines and serial dating. It's a very, very good technology. One of the downsides, however, is that it is a very spot treatment, so this isn't going to be very good if you need to decorate or coat a wide area. It might be not conducive to your cycle time in your process. Another technology is what we call our variable chemistry plasma. Really what that is it's a fancy word for where instead of just using air, we're actually using some kind of a gas chemistry in conjunction with air or not to create the discharge. So here's actually an example of using argon into the head. It could be nitrogen, it could be helium. And the question is why would we use that? Why would we use that over air? There's a couple reasons why. There are some materials out there that are just so very, very heat sensitive that they can't handle any kind of increase in heat or on the surface. Maybe a very thin film would be an example where you just need to spot treat. We can run, for example, CO2 through the system, so that way it's not as warm that comes out of the system. I also mentioned fluoropolymers once or twice in this presentation. They need a little bit of a boost in surface energy because they start so low. So the variable chemistry plasma does a very good job at helping us increase that dyne level because the functionalization piece is key. And another really great application for this, and I think sometimes it's overlooked, is in a lab environment. If you work with a lot of different substrates and you want something that's very versatile, a variable chemistry plasma is nice because you can actually introduce different types of gases into the mix, so that way you basically have a treater that can do many things for many different applications. And then the fourth and final type of atmospheric technology is what we call a flame treatment. It's an ionization of natural gas or propane. What you see is a very high velocity discharge coming out of the head. And there's a couple of really neat benefits to this type of technology. It can handle very high speeds. You literally can design this head into any width you want. There's really no limitation to it. It just increases in complexity, of course, when you get larger and larger. But it also has a nice long-lasting and uniform treatment. So in a perfect world, you want to treat right before the bonding, the coating, or the ink is cured, but that doesn't always work in everyone's application. So if you're looking for something that could potentially treat and maybe need to sit off to the side for a few hours, a few days, you're always going to want to test this before committing to it. A flame treater is going to do a very, very good job of treating that substrate for a longer time. And then one of the most important pieces to point out about flame treatment is that it can handle a lot of contours. So you'll see that this substrate is actually a couple inches away from the actual discharge head, and that's very common when we use this technology. It's used a lot in automotive where we have a lot of contours. It's used a lot in decorating as well, or wider substrates that we just need to be able to cover a wider area in a quicker amount of time. And just to kind of go into that in a little bit more detail, you'll see this now on a 6-axis robot. And I would kind of like to point out, if any of you have worked with flame treating equipment in the past, some of the benefits of using something that is designed for surface treatment, maybe not kind of an off-the-shelf type of system. We use what we call a drilled port burner. And a drilled port burner creates what we call the high-velocity flame discharge. If you could look at this drilled port burner from the side, you'd actually see that they're conical in shape, and what that does is it forces that flame to come out at a certain velocity no matter where you're at inside the burner. So let's just say you had 100 millimeters of treat width, you truly get 100 millimeters from edge to edge, which is very important for repeatability and that you don't need to worry about your surface treatment changing as you go different speeds and as you're working with different types of materials. A more traditional burner, if you've ever worked with flame treating before, is called a ribbon burner. You'll kind of see the photo here in the bottom right hand of your screen. So you can see very quickly some of the benefits of going to the drilled port burner. Ribbon burner does have a lot more variability to it. And if you're looking to invest in a piece of equipment like this, the drilled port burner you can clean, which is huge. You don't have to throw away the burner when it's all clogged up. And a ribbon burner, unfortunately, is a welded together piece and doesn't allow you to clean it in any way. So kind of, you've seen all of these systems integrated in a little different way throughout the program, but I'm also going to show you how we actually look into integration, how you'd actually integrate this in your line and what that would look like for your process. So I mentioned very briefly, how long does treatment last? I get this question every single day. It's a great question to ask. It is going to vary. Unfortunately, there's no magical chart. If you ever see one, I would question the person who made it, because surface treatment will wear off over time regardless of the technology and regardless of the material you're working with. And this is true to atmospheric plasma or flame treaters. There are materials out there that we know tend to be have a shorter lifespan than others. So in a perfect world, you're going to want to treat right before you apply the coating and cure. Storage is never recommended. Like I mentioned, if you needed to, it's worth looking into and doing a longevity study, but we don't recommend storing. And of course, handling also is going to accelerate that degradation process. So using clean latex gloves after treatment and before the coating is applied is really key to not recontaminating the surface. A couple different ways you can then integrate as you're thinking, okay, how do I get it as close to my UV curing process as possible? You can do it offline. You could use these systems over conveyor. I mentioned integrating into existing equipment. You'll see in the bottom right-hand corner there's a picture of a blown ion system treating a folding carton. This was an application where there was a folding carton line, a UV cured coating on the outside of that carton. The customer was having a really hard time getting good bond strength. They were having customer complaints in product that was shipped back to their facility. They were able to introduce a very small little discharge head and overcome that problem by not actually adding another step to their process, which was huge. That can be very, very costly and time consuming. You always put it over an indexing system, and of course, if the shape is very complex or if your cycle time is important, integrating it with a 6-axis robot is not a problem for any of these technologies. And then the other little plug here I'll give you, if you're ever thinking of one of these, they're going to be a really good technology, but you're just kind of in a small scale environment, you can always ramp them up and implement them on a robot later on, which is nice. You don't have to invest in 2 different pieces of equipment. Some considerations I mentioned, flame treatment does a really good job of working with a lot of different types of contours. You'll see a photo here on the right hand of your screen. That's actually an automotive dashboard, so you can think of all the different contours. I believe that was an ABS substrate that they were treating prior to a leather wrapping application. But if you have a lot of complex geometry, flame treatment's going to be a great fit. If you have a very focused path, if you're printing a date code, if you're putting an adhesive down, typically the plasma treatment heads are going to be the best fit for those applications. And then, of course, there is lots of different head designs as well as head quantities. So if you needed to treat different sides of a bottle, or if you needed to treat multiple trays of medical devices as they're coming down the line, you can integrate multiple heads. And then, of course, from a safety as well as a repeatability standpoint, it's really important to ask, okay, how are we going to actually remotely control this? And all of these pieces of equipment do allow you to do that, but that's going to be a really key feature when you're asking yourself as you're integrating plasma into a process. I mean, great, I can push the start and stop button in a trial, but how is this going to actually work in production? I'm not going to have someone necessarily standing right there doing that. And all of these pieces of equipment allows you to remotely control it, as well as remotely, and some of them, log faults and talk back to the line if something were to go awry. So that kind of ties me into some of our advancements that we've been making in plasma treating technology. If you're familiar with it but maybe haven't been at the forefront of it lately, one of the huge things that Enercon specifically has been developing and you've been seeing out there in the market is the data collection, especially in medical device manufacturing, but we understand this is becoming more and more of a demand in a lot of different industries, is being able to not only know that the system is running when someone's physically not standing there, but also being able to log information, log faults, log run data, be able to externally monitor the airflow, the plasma, what we call plasma integrity monitoring. It also measures incoming line voltage and things like that. And with that data, not only can you collect it, maybe give it to your customer, keep it for yourself if you ever needed to lean back on it, It also helps you if you need to do some troubleshooting, which is huge. That's going to save time on your operator's end. There's even an on-screen troubleshooting built into a lot of these treaters in multiple languages as well. So even if you were to integrate it, let's say, in an English-speaking facility but needed to ship it to a Spanish-speaking facility, switching it out is not a problem at all. The idea is to keep this user-friendly. Not everyone's familiar with plasma. I'm guessing the audience here today are the ones that are making these decisions, but those who are working on the floor aren't always the ones who know exactly what it's doing, so we don't want to make this any more complicated than it needs to be for those who are on the floor. So I'm going to do a little bit of a review here, and then I will be opening up the floor to questions. We'll kind of go through that. If you can think of anything related to the topics here today or even beyond, I'd be happy to answer. So kind of just to recap, we've got plasma and flame surface treatment are an inline solution. It's not a batch process. It's used to treat in line with your current existing process or a new process. The three things it does, and this is a huge takeaway if you're brand new to surface treatment, is it cleans the surface, it micro etches the surface, and it functionalizes the surface. Those are the three things that this technology does. Your process and your application are going to demand what route we go. There's not necessarily one set path for each application out there, and we understand everyone's needs are a little different. And really the best place to integrate a flame or plasma piece of equipment is directly before you apply the ink coating adhesive and cure it. So in a perfect world, that's where we'd like to see that happen. And once again, thank you for attending today. I'm going to open up the floor for questions. If you would prefer to type them into your chat box right now, I'd be happy to go through them. If you'd prefer to ask me offline, all of my contact information is on that screen. Send me an email, give me a call, call anyone on our team. All right. So we'll give you guys just a minute or two to type a couple questions in here, and we'll go through as many as I can. I'll try to be cognizant of our time here too, so if I understand if you do need to leave and, like I said, want to contact me offline, I'd be happy to help, and I will get to them in turn. So I've got the first question here I have is related to lab testing. So I know I briefly spoke about this a few slides back. You might be thinking of a specific application that you have, and maybe it's a substrate that's new to you, or maybe you're having some adhesion challenges and going, okay, great, now what do I do with that? So the first thing I would recommend is to give me a call, give our team a call, connect with us online, and we'll set up a lab trial for you. So I mentioned our headquarters are in Wisconsin. We run a full-time lab there where we treat material 5 days a week, and it's specifically designed for customer use only. You're welcome to visit during the trial, but basically we'll get an idea of your parameters. What are your cycle times? Where on the part do you need to treat? What other limitations are we working with? We're going to treat those substrates, give you a full report of what we find, beginning and ending surface energy. We can measure polarity and that kind of thing, and ultimately ship this material back to you overnight for you to test. And overnight is key because we know that surface energy does wear off over time, and hopefully see some adhesion improvement, and then can kind of talk a little bit further on what that means and how that's going to look in your application. So if you're at any all interested in any kind of lab trial, it's completely free. So please give me a call. I'd be happy to walk you through it. And I mentioned you're more than welcome to visit in Wisconsin. It is gorgeous this time of year too. So if you've ever been in the mood to visit, we love it when customers come in as well. I'm going to answer a couple more questions. Thank you so much for everyone who's put some on the board here. What process is more efficient for surface activation, CO2 blasting or flame treatment? So that's actually a very good question. So it's going to be very dependent on the material, and I'll give you a couple examples. So flame treatment is a very universal type of technology. It treats quite a variety of plastics. We know it does a great job at cleaning, so metals are a really, really good substrate for that to work with. Some of the limitations of flame, however, is when we get into rubbers and silicones or very heat-sensitive materials, we know it actually doesn't do a very good job. So actually, a CO2 style variable chemistry plasma treater is going to do a really good job. There's a chance, let's just say you're working with polypropylene, where both of them would work perfectly fine. So then the next question would be, okay, they both activate the surface, which one's going to be more conducive to your application, and what kind of cycle times are you looking for, and maybe we're able to raise it to a similar dyne level, you might ultimately have more than one solution. So thanks for the question. Is HDPE different than PE? Yes. So high-density polyethylene versus polyethylene, yes, they are two different substrates. We do work with both of them. We do find that HDPE and LDPE, so low-density polyethylene, are probably more common in our facility. They typically have a lower starting surface energy level than just straight polyethylene. So if you are working with HDPE, we have quite a bit of experience working with it, a lot in the natural gas pipeline industry and marking it with inkjet. So let me know if you have something you'd like me to work with with that particular substrate. Oh, this is a great question. Okay, are there any personal hazards to the blown ion? And I'll answer that question, and I'll also answer that related to all of the equipment. So the answer is yes. All of these systems, while they're atmospheric, you could potentially be harmed by touching it. So specifically to the blown ion system, it is internally grounded. But it does generate heat. So it could be a potential burn hazard. We recommend with all of these systems that you do guard the head, so a light curtain, a physical barrier. It doesn't have to be very complex so that an operator doesn't accidentally come in contact with the discharge. This is specifically very important for any of the systems that have an alternating current and they're looking for ground, because you'd potentially get an arc or a shock from the ground. So you do want to guard it. We also recommended that these are used in a well-ventilated area or a dedicated hood over the system. Part of the process is we're cleaning. We don't know what we're cleaning off the surface, so we want to make sure that is evacuated from the work area. Let's see, how do atmospheric treatment compare in terms of dyne level to vacuum plasma? It's similar in some cases, similar if it's an easier to treat material. If it was a very low surface energy, I'll go back to my fluoropolymer example again. Vacuum plasma actually does a very, very good job of raising the dyne level. Atmospheric plasma, we'd have to use a gas chemistry, or it wouldn't be comparing apples to apples with that particular substrate. But if it was maybe more of the easier to treat materials, you're going to see a very similar dyne level outcome. Now, one of the benefits of vacuum plasma is that it can treat a very complex shape inside of a box. I'm using very crude words here, but envision an oversized microwave. And you put the part in and you shut the door, and the plasma is going to bounce all over. So if you're just trying to treat one part and it's very, very complex, vacuum plasma is probably going to be a very, very good fit for it. Atmospheric does require line of sight. That's very important, and that it is line of sight. It's not going to treat 360 degrees of a sphere unless you were to physically move the part or move the head. But they can be compared. They can be similar in dyne level. It just really depends on the material. Another piece that I didn't touch that much on is the web treating end of things. So I showed a lot of pictures of objects, but obviously treating films and foils in an inline process is another piece of what we do. And so it sounds like we have a question. We have an inline plasma treater. The web we are treating runs over either an aluminum or a steel roll before lamination. And the question is, how much treatment degradation should we expect after the web moves over one of those rolls? So in an inline process, if you've got a plasma treater, you're plasma treating typically within seconds, within minutes of the lamination, typically. I mean, I guess everyone's process could be a little different. That is normally not going to be a problem. Most of our inline printing, lamination, and coating lines, surface degradation is not going to be a factor because we're talking in terms of seconds, even minutes. Where it is going to be a problem is if, let's say, you were to buy material that has been treated upon extrusion and it has been sitting there for a few months, and now you're going to go put it on your laminating line and you don't have a plasma treater or a corona treater, then you may be potentially trying to coat or print on a material that surface energy has degraded too much because it's been quite a while since it's come from the extruder. So normally the best practice when we're working with an inline web is to put what we call a bump treater on, and that could be a corona treater and that could be a plasma treater. I didn't include any slides of what those pieces of equipment look like here today, but let me know offline. I'd be happy to give you a little bit more information on that. Health and safety issues related to radiation. So actually this is a good question. It has something that came up not too long ago. So when you do work with UV light, one of the really important factors is that you don't, that you have some kind of guarding from your operator to the UV light because there's radiation exposure. With these systems, unless, like a best way to put it, unless you were staring straight up into the discharge head, there is no health or safety issues related to running it in a normal working environment. Probably the biggest piece, I mentioned the guarding already and the ventilation, is also some form of ear protection. They all have different decibel levels, but if an operator were going to be working near one of these treaters for long periods of time, we probably would recommend some kind of ear protection, but no specific kind of glassware needs to be, or curtains need to be developed to protect the operator. But that's a great question. You're looking at, got a question here on printing UV inks on plastic bottles. Does HDPE plastic need different treatment than Triton? Whenever you change your substrate, it is always good to re-qualify not only with your ink, but also with the treatment step. The reason why I say that, it even goes beyond different types of plastics. Let's even just say you're getting your HDPE bottles from one supplier and now you're getting it from another. It's always good to requalify it. You can do it very quickly with a dyeing test or a quick little DOE to ensure that you're working with the right surface energies before and after, because we've seen that even a few dynes can give you a change in adhesion. There's going to be a minimum dye level depending on your application that you need to meet, and UV is typically pretty high in order to get that true adhesion. And then also the next question you have to ask is, what does good adhesion mean to me? I mentioned early on a medical device coming apart is probably has much more stringent policies on adhesion than maybe something that's more of a decorative UV of a coating on something. So it's always good to ask yourself, how do we measure that and make sure that we are consistent throughout. But I would definitely say it's probably worth evaluating both types of plastics. We got another a film lamination question. Film lamination over a litho ink printed on a flexible PVC. So this is, I'm guessing this is an unconverted gift card material. So it says you're using lower when using a chronotreater versus non-treated before printing. We found this very unexpected, and can you offer any possible explanation? So a couple things that could be going on, and it probably requires a little bit more in-depth look here. I've had the question before where bond strength actually decreases with treatment. Few things that flexible PVC, this might be what's going on. So I mentioned that we are treating, one of the things that you're doing is you're cleaning the substrate. What could be going on, and I actually can think of a time where I've worked with a customer on a very similar application, is that you have paved the path for something to migrate to the surface that wasn't there before. So when you're actually bonding, when you're actually laminating, I apologize, laminating, you're no longer laminating to the raw PVC. You might be laminating to whatever has migrated to the surface. That's one explanation. Another is, and this is actually a really good point to bring up, surface, you can over-treat a substrate where you're actually damaging it on a molecular level. So sometimes we always think more is better, and this is really where the lab comes into play and helps you with your specific application, we might be over-treating it. It's just a thought. Definitely, if you'd like to explore that more, let me know. I'd be happy to set up a trial, but those are two possible explanations I could see, and unless there's some other variable that isn't listed. What effects would treatment have on a printed sheet before applying a UV-cured coating over UV inks and an aqueous coating? So if it's on a sheet before applying the coating, so when you're, if I'm understanding the question correctly, if you are trying to cure UV over UV, this is actually a very good question for the ink and coating formulator as well as your supplier of your UV coating or UV curing equipment. I will be honest, I'm not an expert in this specifically what you need to do, but what I do know is that typically these applications, you need to only partially cure the first layer, and then when you apply the next layer, then you fully cure it, and it's done at different wavelengths. So normally if you're trying to print, I can think of one customer that was doing this. I mean, tried surface treating and it didn't help in this case. If you're trying to print or coat on an already UV cured substrate, it's very difficult to do. So I would say reach out to your ink and coating supplier as well as your UV equipment manufacturer and see if they could help with that. But if that does not help, we could look at surface treatment as a possible solution. Let's see here. Is plasma treatment suitable for textile application? For example, to improve adhesion to a polyester nylon? Yes, absolutely. Textile applications are a key thing that we work with on our web treating side of things. So if you are trying to coat it, it is a little bit more of a challenge to measure what we call surface energy because typically textiles are absorbent. Not in all cases, but yes, absolutely, you could treat inline, whether we've done it everywhere from just the thread or the yarn all the way up to an already woven material. And actually have quite a whole team here that has quite a bit of experience on working with those kinds of materials, so let me know. Actually, this is a great one. Do you work with pre-treatment on glass for printing UV ink? So glass is an interesting substrate because it already has a very high surface energy. Normally it's not a functionalization piece that we're dealing with. What we're dealing with is that the substrate itself is very slick. It's very flat. It doesn't have a lot of physical surface topography. So it's very important when you're printing on glass that you are using the correct UV ink. That is like the #1 thing to start with. And once you have ensured that you're using the right ink and you're still maybe not having the adhesion that you're looking for, then what's very important to do is to look at the cleanliness of the surface and ultimately what kind of adhesion that you want to achieve. I can think of everything from printing date codes on beer bottles all the way up through working with automotive glass, and all of those adhesion requirements are very, very different. So I would say start with the ink, ensure the ink is the correct formulation, and then look at surface treatment as a secondary piece there. Can you measure the curing? So the curing of an actual substrate is going to be related to the UV equipment. If you're looking at measuring the adhesion, there's a couple different tests that you can use. If it was a coating, you could use a traditional crosshatch test, and that would allow you to see what kind of adhesion you have throughout the product that between the coating and the substrate. If you had if you were, let's just say you're digitally printing ink, you could use just a tape test on that. And another option would be if it's a bond strength of an adhesive, so you're measuring if the adhesive has adhered well to the surface, then you could use a pull strength test. If you're trying to detect if the actual ink or coating or adhesive is cured all the way, that would be a little bit more of a question for the UV equipment supplier, and they'd be able to give you some guidance on that. Another question here, just wants a clarification. Contact with aluminum or steel after treatment is not as critical as time since the treatment. And I think this refers back to a question from earlier. So having contact with a ground roll or a idler roll, so aluminum or steel after treatment, would be a problem if those had some level of contamination. We do know the more contact a surface has prior to applying the ink or the adhesive down, the greater the chance that you're going to be not only contaminated and decrease your dyeing level, but it doesn't necessarily mean, and I'm going to use very round numbers here, it doesn't necessarily mean you've treated to a 50 dyeing and now you've come in contact with one roller. Now it dropped to 10 dynes and now it dropped in another 10. It's not a linear process like that. I'd probably actually be more concerned about the contamination, potential contamination on the rolls, and I'd be more concerned if let's say your line were to stop and material were to sit on there for long periods of time. I'd probably be more concerned about those two things. But yeah, the more times you come in contact with a treated surface, the more chance there is for potential decrease in dyeing as well as contamination. So if there's any way to look at your process and move the plasma or coating and treating equipment as close to the lamination process, the better. That's just a really good practice to do it that way. Another question here, and I know we're kind of going over on time, so if you have to jump out, I completely understand. I'll go as long as you guys have questions. What is your experience treating fiber-based materials such as cardboard, paper, etc.? So an uncoated. To be honest, I can't say we work with that a lot. In a lot of cases, we work with like folding cartons where there's actually a coated side. So we're actually dealing with the coating not adhering well to, let's say, the uncoated side of a folding carton. In a lot of cases, the cardboard and paper don't typically need treatment unless there's some sort of an additive or coating on top of it. Doesn't necessarily mean that we can't treat it. I would say we probably don't see it that frequently unless it's a coated paper of some kind in our lab for testing. And I don't see any more questions, so like I mentioned, my screen's up there. If you'd like to contact me offline, please do.
Okay, thank you very much, Sarah. I'd like to take this time to thank you, Sarah, for taking time out of your day to give this presentation. I'd also like to thank RadTech for helping to organize these webinars and everyone for joining in today. So I hope everyone has a great rest of the day.
Thank you.
Thank you. Bye, everyone.